somewhere in a flat, wet stretch of eastern England sits a university city that began 2,000 years ago as a modest market town, and few places this size have left a comparable mark on the modern world. An apple falls in a garden nearby, and gravity gets explained. A young naturalist studies here before boarding a ship called the Beagle. A mathematician sits in a small room here and sketches, on paper, the theoretical blueprint for every computer ever built. Newton, Darwin, Turing, three names that reshaped how humans understand the universe, life, and thought itself, all tied to the same river, the same stone courtyards, the same few streets. This is not just the story of a university. It is the story of how one small English town kept becoming the place where the modern world got worked out. Let us go back to where it started. Chapter 1. Duroliponte to Grantebrycge. The three names on this video's thumbnail were still more than 1,000 years away from being born. What existed here first was much smaller and far less romantic. A river, a narrow crossing, and a question every army in this part of the world eventually had to answer. Where can we get to the other side? Strip away every modern road and railway from a map of eastern England, and the reason becomes obvious. This is flat, low, wet country, cut by slow rivers draining toward the North Sea. The kind of landscape where moving an army or a loaded cart depended entirely on finding a place the water could be crossed without boats. Near what is now the centre of Cambridge, the River Cam narrowed just enough, and the ground on both banks stayed firm enough underfoot to make that crossing possible. Everything that follows in this story, the colleges, the laboratories, the Nobel Prizes, ultimately traces back to that one narrow strip of solid earth. Roman surveyors found it within a few decades of the invasion of Britain in 43 AD. A document called the Ravenna Cosmography, compiled around the 7th century from older Roman source material, lists a place called Duroliponte along the road network of the province. Most historians working on Roman Britain accept Duroliponte as the likely Roman name for this site, though the identification rests on geography and road distances rather than any inscription found on the ground that names the place directly. So it remains an educated conclusion rather than a certainty. What the ground itself has confirmed, through decades of excavation on Castle Hill on the north bank of the river, is a fort. Its ditches and post holes, traced by archaeologists digging beneath the modern street plan, sitting exactly where a garrison protecting a river crossing would need to sit. This was never one of the glittering cities of Roman Britain. Nothing like the Forum and bathhouses of Londinium downriver on the Thames. It was smaller and more practical. A garrison, a supply depot, a junction where a road later historians call the Via Divana crossed the river on its way north toward Lincoln. Coins, pottery fragments, and the remains of timber granaries recovered from Castle Hill sketch a picture of ordinary military life. Soldiers drawing pay, merchants selling to them, craftsmen mending tools and harness. Roman garrisons in Britain were routinely drawn from across the empire, and while the specific origins of the men stationed at Duroliponte are not clearly recorded in any single surviving document, broader evidence from Roman Britain makes it plausible that at least some of these soldiers had never seen England before arriving here. Within a generation, a civilian settlement grew up alongside the fort, on the south bank of the river, where merchants and craftsmen found it easier to build than inside a walled military compound. Then, Rome's grip on Britain loosened, the way it loosened almost everywhere along its northern frontier during the 4th and early 5th centuries. Military pay stopped arriving reliably. Coin use, once common enough to litter the archaeological record, becomes rare in the layers dating from this period. Buildings that once held granaries and workshops were abandoned, their roofs collapsing, their walls slowly sinking under wind-blown soil and decades of undisturbed vegetation. A pattern. Excavators across former Roman Britain have learned to recognize almost anywhere they dig deep enough. Duroliponte did not fall in a single dramatic battle that any chronicle bothered to record. It simply stopped being maintained, the way an unused building stops being maintained, until there was less a ruined city here than a set of grass-covered mounds, later generations no longer fully understood. The people who eventually resettled this stretch of river were not the kind of people who valued walled forts or paved roads. Anglo-Saxon farmers, arriving and consolidating their presence across the 6th and 7th centuries, built on the south bank rather than inside the old Roman defences, in the area that would grow into Cambridge's medieval town centre. They called the settlement Grantebrycge, the bridge over the Granta, a name built directly from the older British name for the river that would eventually shorten into Cam. Notice what the name preserves and what it discards. Not the fort, not the roads the Romans had been so proud of. The bridge, and nothing else. Because the bridge was the only part of the Roman inheritance that still mattered to the people living there now. For roughly 2 centuries, Grantebrycge grew slowly and left barely a mark on the written record. The kind of place chroniclers mention only when something goes wrong. Something went wrong in 875. The Anglo-Saxon Chronicle records that a Viking army, after years of raiding and campaigning across eastern England, moved into Grantebrycge that year and wintered there, digging in along the riverbank rather than withdrawing to Scandinavia as earlier raiding parties usually had. A farmer working land near that river in the autumn of 875 would have watched an army speaking an unfamiliar language build fortifications on the opposite bank and settle in for the cold months. With no clear sign they intended to leave in spring. They did not leave in spring. Within a few years, the region around Grantebrycge had become part of what historians call the Danelaw, the portion of England living under Scandinavian rule and Scandinavian law, rather than the law of the West Saxon kings further south. The reversal came a generation later, in the early 10th century, as King Edward the Elder pushed to reclaim the Danelaw territory by territory. English forces retook Cambridge, and the town was absorbed back into a reunified English kingdom. Its river crossing now serving a very different set of rulers than the ones who had built the original fort 900 years earlier. By the time of the Domesday Survey commissioned by William the Conqueror in 1086, Grantebrycge, its name already drifting toward the shorter form, Cambridge, was recorded as the head town of its own shire, with a bridge, a market, and enough taxable property to matter to a Norman king assessing what he had just conquered. The fort, the bridge, the winter camp, the shire town. Not one of these involved a single scholar or a single book. For roughly 8 centuries after a Roman surveyor first judged this stretch of river crossable, Cambridge existed because armies needed it, traders needed it, and kings needed to control it. Nothing more romantic than that. It would be an overstatement to claim every single power struggle in eastern England ran through this exact spot. What can be said more carefully is that many of those who wanted to control this part of the country had to reckon with this crossing, one way or another, for the better part of 1,000 years. But every one of those centuries left behind exactly what the future university would eventually require without knowing it. A stable crossing, a functioning local economy, and a town accustomed to housing outsiders passing through on other people's business. When the first frightened scholars arrived here from Oxford early in the 13th century, they were not choosing an empty field. They were choosing a crossing point that had already spent 800 years proving it could survive almost anything thrown at it. Newton had not been born. Darwin had not been born. Turing was 700 years from being born. But the ground that would eventually hold all three of them was already exactly where it needed to be. Chapter 2. Scholars flee Oxford. 1209. It is the year 1209, and Oxford has just become the most dangerous place in England to be a scholar. The trouble began. According to chronicle accounts, written by figures such as Roger of Wendover, working in the following decades, with the death of a woman in Oxford. Most surviving versions describing it as the result of a dispute or an accident involving a clerk rather than a deliberate murder. Though the thinness of contemporary evidence means historians reconstructing the event today are working from fragments and later retellings, rather than a full eyewitness record. The clerk responsible fled the town before anyone could arrest him. What happened next turned a local tragedy into a national one. Unable to lay hands on the man actually involved, the town authorities seized a small number of other scholars who had no connection whatsoever to the killing and hanged them. An act Chronicle sources describe as carried out with the cooperation, or at least the acquiescence, of Oxford's civic leadership. For the loose community of masters and students already gathering in Oxford, a body that had been forming informally for perhaps a generation before this. The message could not have been clearer. A scholar in Oxford could be executed for a crime someone else committed, with no meaningful protection from either the town or the Crown. Teaching across Oxford effectively stopped. Some masters relocated to Reading. Some crossed the Channel to Paris, where a far more established university already operated under its own long negotiated privileges, and a significant number, for reasons no single surviving document fully explains, chose to travel roughly 80 miles northeast instead, to a market town on the River Cam that had no university at all, but did offer the two things that mattered most in that moment: distance from Oxford's danger and a local economy stable enough to feed and house them. These were educated, mobile men with real options, Paris chief among them, choosing Cambridge instead. A town with no university tradition of its own. Says something about the calculations they were making, even if none of them would have described it in those terms. 800 years of quiet, reliable survival is not a small thing to build on. This is why 1209 is treated, both by Cambridge's own institutional tradition and by most modern historians of English universities, as the effective founding moment, not a royal charter, not a bishop's grand design, a group of frightened, angry academics who needed somewhere else to work. The years immediately following are thin on documentation, and honesty here matters more than false precision. We do not know exactly how many scholars arrived in that first wave, or how quickly formal teaching resumed once they did. What the surviving record does show is the shape their community gradually took. Masters rented halls and rooms from local landlords, teaching students grammar, logic, and theology, much as they had in Oxford, without yet answering to any single governing authority over the whole group. Religious orders arrived quickly to serve this growing population of scholars. Franciscan friars established a house in Cambridge by 1226, and Dominican friars followed within little more than a decade. Both orders building their own reputation for scholarship that would eventually feed directly into the university's teaching. Relations between these scholars and the ordinary people of Cambridge were tense almost from the start, and that tension shaped the town for centuries afterward. Landlords, facing a captive market of students who needed lodging, often charged accordingly. Fights between town residents and university men were frequent enough to require repeated royal intervention. In 1231, King Henry III issued an order addressing complaints from Cambridge scholars about excessive rents, and in the same period, took steps to expel people who were using the university's growing reputation as cover, while not genuinely studying at all. That royal order stands today as one of the earliest solid pieces of evidence that a recognized studium, a formally acknowledged community of scholars, existed in Cambridge by that date. A community distressed enough by rent gouging to petition the Crown for relief was, by definition, a community that had already grown large and permanent enough to matter economically to the landlords exploiting it. 2 years later, in 1233, papal recognition is generally understood to have extended to Cambridge scholars certain protections already granted to students in Paris, including safe conduct while travelling between Cambridge and their home diocese, a privilege attributed in most accounts to Pope Gregory IX. Though the surviving documentation from this specific period is sparse enough that historians treat the precise wording and scope of that recognition with some caution rather than quoting it as settled fact. What mattered practically was the signal it sent. Cambridge was no longer simply a refuge town where displaced Oxford scholars happened to be teaching. It was being treated, at the highest level the medieval church could offer, as a legitimate centre of learning in its own right. For its first 7 decades, however, Cambridge had no colleges in the sense we would recognise today. Masters and students lived scattered across rented halls and hostels with no endowed buildings, no permanent income, and no institutional identity beyond a loose federation of agreed rules for teaching and examination. A hall could vanish the moment its lease ended, or its landlord decided to raise the rent. The entire academic community existed, in a very real sense, at the mercy of Cambridge's private housing market, a precarious arrangement that made the university's long-term survival far less certain than its later prestige might suggest. That changed in 1284. Hugo de Balsham, Bishop of Ely, had already tried a smaller experiment a few years earlier, housing a handful of scholars alongside the Augustinian canons of the Hospital of St. John in Cambridge, hoping the two communities might share resources peacefully. They did not. Contemporary and later accounts describe persistent friction between the university men and the canons. Disagreements sharp enough that Balsham eventually concluded scholars needed a home entirely their own. His solution was Peterhouse, founded that year as an endowed institution with its own buildings, its own income from land and property, and its own permanent community of fellows living under a common rule. The first Cambridge college in the modern sense of that word. A medieval college was not simply a dormitory, and the difference actually matters for everything that comes later in this story. It was an endowed corporation, holding land that generated income indefinitely, governed by its own statutes, electing its own head and its own fellows, and capable of surviving the death of its founder without losing a single privilege it had been granted. Once the land was secured and the charter written, a college could outlast wars, outlast plagues, and outlast every person who had ever set foot in its founding ceremony. That durability, more than any single scholar's brilliance, is the specific mechanism that let Cambridge survive the coming century largely intact. While so much of the rest of medieval England did not, Peterhouse would not remain alone for long. What followed within a few decades was not simply a slow, steady expansion of academic ambition. It was a direct response to a catastrophe that killed roughly a third of England's population and left the church desperately short of trained clergy to replace those it had lost. A crisis that, strangely, would end up building most of the college system. A young Isaac Newton would one day inherit. Chapter 3: Colleges, Kings, and the Medieval Golden Age. 4 new colleges in 5 years. That is the strange arithmetic of catastrophe that defines Cambridge's 14th century, and understanding why requires going back to the disease that made it necessary. The Black Death reached Cambridge in the summer of 1349. Most likely carried inland along the same trade routes that brought wool and grain through the port towns of eastern England. And it did not spare scholars simply because they spent their days studying theology. Historians place Cambridge's losses in that outbreak in a similar range to other English towns of comparable size. Somewhere between a third and a half of the population dead within a matter of months. Though precise figures for any individual medieval town are difficult to establish with confidence, given the patchy record-keeping of the period, monastic communities and parish clergy were hit especially hard, partly because communal living made avoiding contagion nearly impossible, and partly because priests were repeatedly called to the bedsides of the dying at exactly the moment the disease was most contagious. The result, across England as a whole, was a severe shortage of trained clergy capable of hearing confession, administering last rites, and running the ordinary business of parish life. That shortage, more than any abstract enthusiasm for learning, explains the burst of new college foundations at Cambridge in the decades immediately following the plague, each one built with the explicit, practical purpose of training replacement clergy as efficiently as possible. Pembroke College was founded in 1347 by Marie de Saint Pol, Countess of Pembroke, just 2 years before the plague's arrival, and would go on to educate generations of clergy through the difficult decades that followed. Gonville Hall, later renamed Gonville and Caius, was founded in 1348, the very year the plague reached England, by a clergyman named Edmund Gonville, who stated his purpose plainly: to train priests for a church that badly needed them. Trinity Hall followed in 1350, founded by the Bishop of Norwich specifically to train canon and civil lawyers. Professions his own diocese had lost heavily to disease. Corpus Christi College, founded in 1352, stands out from this pattern in one important respect. It was funded not by a bishop or a noble, but by 2 Cambridge town guilds, the Guild of Corpus Christi and the Guild of the Blessed Virgin Mary. Ordinary tradesmen and townspeople who had watched the clergy shortage firsthand and decided to fund a solution themselves. The practical effect of all this went well beyond training more priests. Each new college added its own endowed land, its own library, its own community of fellows conducting research alongside their teaching duties, quietly multiplying the institutional capacity that later centuries would inherit. The university did not simply survive the Black Death. In a grim and practical sense, the disease helped build it, by creating urgent, immediate demand for exactly the kind of trained, endowed institution Cambridge was learning to produce. The most visually spectacular addition to medieval Cambridge, though, came from the crown rather than the church's staffing crisis. In 1441, King Henry VI founded King's College, intending from the very beginning to make it the grandest religious and educational statement Cambridge had yet seen. Its centerpiece, King's College Chapel, took the better part of a century to complete. Reginald Ely served as the original master mason under Henry VI, but construction stalled repeatedly through the political chaos of the Wars of the Roses, funding drying up whenever the crown itself was fighting for survival. Work eventually resumed under Richard III and then Henry VII, and the final stage of construction, the astonishing fan-vaulted ceiling that still draws visitors from around the world, was completed under master mason John Wastel between roughly 1508 and 1512, with the chapel's magnificent stained glass windows not finished until 1531, under Henry VIII, nearly 90 years after the first stone was laid. 4 different kings, 2 of them locked in a civil war that determined which royal house would even survive to keep paying for it, all had a hand in finishing the same building. Very few construction projects anywhere in history have survived that much political turnover and still ended up this coherent and standing beneath that fan-vaulted ceiling today. A canopy of stone carved into radiating ribs that architectural historians still study as one of the high points of English medieval engineering. It is easy to forget how close the whole project came to simply stalling out for good more than once. Queen's College added its own strange footnote to Cambridge's medieval story. Founded in 1448 by Margaret of Anjou, wife of Henry VI. It was refounded and expanded in 1465 by Elizabeth Woodville, wife of the rival king Edward IV. Two queens, from opposite sides of the same civil war, leaving their mark on the same college within a single generation. Political power in England shifted violently and often across these decades. But the colleges themselves, once endowed with land and legal protection, tended to survive whichever monarch or noble family had founded them, a pattern that would repeat again and again across Cambridge's history. By the early 16th century, Cambridge had assembled the essential shape it would carry into the modern era, a cluster of independent, self-governing colleges, each with its own buildings, its own income, and its own community, loosely bound together under the wider university for matters of degrees and examinations. It had been shaped less by any single coherent plan than by student riots, a papal privilege, a catastrophic plague, and the shifting fortunes of a civil war. An institution built, quite literally, out of crisis after crisis. Hugo de Balsham had been trying to solve a housing dispute. Edmund Gonville had been trying to train priests. Henry VI had been trying to build a monument to his own piety. Between them, without any of them intending it, they had created exactly the kind of endowed, self-sustaining institution that would one day give a young mathematician the freedom to sit alone in a room at Trinity College and think, for months at a stretch, about gravity, light, and the structure of the universe itself. That freedom would need one more upheaval first, and this one would cost some of Cambridge's own scholars their lives. Chapter 4. Reformation Fire. Three men once argued over forbidden books together in a Cambridge tavern. All three would later be burned at the stake for the ideas they developed there. By the early 1500s, Lady Margaret Beaufort, mother of King Henry VII, had already funded the founding of Christ's College in 1505 and St. John's College in 1511, quietly reshaping Cambridge's landscape through piety and family wealth. Neither foundation could have anticipated what was about to move through the university within a single generation. In 1511, the Dutch humanist scholar Desiderius Erasmus arrived at Queen's College to teach Greek and theology. Already one of the most respected scholars in Europe, his roughly 3 years at Cambridge coincided with his work on a new Greek edition of the New Testament, a project that would later give reformers across Europe direct access to scripture outside the authority of the Latin Vulgate the Catholic Church had relied on for centuries. Erasmus's own surviving letters make his personal discomfort at Cambridge fairly clear, complaining to friends about the local ale, which he found close to undrinkable, and about winters he considered miserable for a man used to the Low Countries. Whatever he thought of the beer, the intellectual environment he helped cultivate at Cambridge outlasted his complaints by centuries, and the Greek scholarship he brought with him gave the next generation of Cambridge scholars tools they had not previously had for reading scripture in its original language. Within a decade of Erasmus leaving, a small group of Cambridge scholars had begun meeting to discuss ideas spreading rapidly out of Germany. The writings of Martin Luther. Local memory has long placed their meeting spot at a tavern known as the White Horse Inn, on a site near what is now Gonville and Caius College. Though the building itself has long since disappeared, and some details of the story, including exactly which building, on exactly which street, rest more on later retelling than on any contemporary record. What is much better documented is who gathered there. Thomas Bilney, a Fellow of Trinity Hall, is credited in multiple historical accounts with convincing Hugh Latimer, at that point a committed defender of traditional Catholic teaching, to embrace reformist ideas instead. Thomas Cranmer, who studied at Jesus College, would go on to become Archbishop of Canterbury and the principal architect of the English Reformation's new liturgy. The cost of these convictions arrived in stages. Bilney was arrested for heresy and burned at the stake in Norwich in 1531. Latimer survived him by more than 2 decades, becoming Bishop of Worcester, before being burned at Oxford in 1555 alongside fellow reformer Nicholas Ridley. Under the Catholic monarch Mary I, Cranmer himself was burned at Oxford the following year, 1556. 3 men who had once argued over forbidden books together in a Cambridge tavern all died for the ideas they developed there. Though notably, none of the executions took place in Cambridge itself. The university's own leadership was not spared either. John Fisher, Bishop of Rochester and Chancellor of Cambridge for over 3 decades, had helped Lady Margaret Beaufort establish both of her colleges and was respected across Europe as a theologian. When King Henry VIII broke from papal authority in order to divorce Catherine of Aragon, Fisher refused to accept the king as supreme head of the church in England. He was executed in 1535, and his death sent an unmistakable message through every college in Cambridge. That theological conviction now carried consequences, reaching even a university's own chancellor. The dissolution of England's monasteries through the late 1530s transferred enormous quantities of monastic land and wealth to the crown, and some of that wealth eventually flowed into Cambridge's colleges through royal grants and purchases. A financial windfall built directly on the closure of institutions that had themselves once educated many of the scholars now benefiting from their disappearance. Trinity College, still one of Cambridge's largest and wealthiest colleges today, was founded by Henry VIII in 1546, drawing partly on property seized from dissolved monastic houses. A foundation that, in a very real sense, used the wreckage of the old religious order to build a new centre of learning, loyal to the crown rather than to Rome. 15 years later, an undistinguished subsizar named Isaac Newton would walk through its gates, having no idea how directly his own college's wealth traced back to this specific, brutal redistribution. By the time Elizabeth I came to the throne in 1558, Cambridge had lived through roughly 2 generations of theological upheaval that had cost several of its own scholars their lives, reshaped its curriculum away from purely Catholic scholasticism, and left it financially transformed by the redistribution of monastic wealth. The university Elizabeth inherited was more explicitly Protestant, more directly bound to the crown, and considerably richer than the one Erasmus had complained about the beer in decades earlier. What Cambridge carried forward from these decades was a lesson it would relearn more than once in the centuries ahead: that ideas debated quietly inside a college room rarely stayed there. They reshaped national religion. They claimed lives. They rewrote the rules under which the university itself was allowed to operate. A century and a half later, a very different kind of idea, born in a different Cambridge room and concerned with gravity rather than scripture, would prove the same point on an even larger scale. And this time the man having it would never be burned for it, only occasionally accused of being too strange to talk to. Chapter 5. The Man Who Explained the Universe. The most productive 18 months in the history of Western science began, almost accidentally, with a university deciding to close its doors. Isaac Newton arrived at Trinity College in June of 1661 as a subsizar, a student of limited means who paid reduced fees in exchange for performing menial tasks for wealthier students and fellows. Cleaning boots, running errands, waiting at table. Nothing about his admission suggested Cambridge was receiving a genius. His early academic record was unremarkable, and the university's official curriculum still leaned heavily on Aristotelian philosophy. A body of thought, Newton, reading well beyond his assigned coursework, had already begun to find unconvincing. What actually changed his trajectory was private study rather than formal instruction. Notebooks surviving from his undergraduate years show him working through the mathematics of René Descartes and the astronomy of Johannes Kepler, far beyond anything his tutors required, developing an understanding of algebra and geometry that quietly outpaced their expectations. By the time he took his bachelor's degree in 1665, Newton had already become one of the most capable mathematicians in England. A fact almost nobody outside a small circle at Trinity yet recognized. Then, in the summer of 1665, an outbreak of bubonic plague reached Cambridge, part of the same wave that would devastate London the following year. The university closed its doors and sent students home to slow the contagion. Newton returned to his family's farm at Woolsthorpe Manor in Lincolnshire, expecting, like everyone else, a temporary disruption to ordinary life. Nobody involved in that decision, made purely as a public health precaution. They could have known they were about to hand one of history's greatest scientific minds 18 uninterrupted months with no lectures, no tutors, and no distractions beyond a farmhouse and a garden. What followed, across roughly 18 months, split between 1665 and 1666, is remembered by historians of science as one of the most productive stretches of solitary thought by a single person in the history of the field, working almost entirely alone, without university libraries or colleagues nearby to argue with. Newton developed the mathematical method he called fluxions, what we now call calculus, discovered independently around the same period by the German mathematician Gottfried Leibniz, a parallel achievement that would later fuel one of the bitterest priority disputes in the history of science. In a darkened room at Woolsthorpe, using a small hole cut in a window shutter to admit a narrow beam of sunlight, Newton passed that beam through a glass prism and began the optical experiments that would eventually convince him white light was not pure at all, but a mixture of every color, separated rather than created by the glass. And somewhere in that same stretch of months, in his mother's garden, he began working through a question that would occupy him for years afterward. The apple story deserves more care than the popular version usually gives it. Late in life, Newton told several people, including the antiquarian William Stukely and his own niece, that watching an apple fall in the Woolsthorpe garden had prompted him to wonder why objects fall straight down rather than sideways, and whether that same force might reach far enough into the sky to hold the moon in its orbit around the Earth. Stukely's account, recorded from a conversation with Newton in 1726, the year before Newton's death, is treated by most historians as broadly credible, since it comes from Newton's own recollection rather than later invention. What almost certainly is later invention is the popular image of the apple striking Newton on the head, a detail absent from every contemporary account and likely added for comic effect long after his death. The real story is quieter, and in its way more remarkable. A working scientist noticing an entirely ordinary event and asking an unusually large question about it. A tree grown from cuttings of that original Woolsthorpe apple tree still stands today outside Trinity College's chapel, planted there long after Newton's death, but tended as a living link to the story. A detail Cambridge itself is careful to describe as symbolic rather than as proof of unbroken botanical continuity. Newton returned once the university reopened, was elected a Fellow of Trinity in 1667, and in 1669, at only 26 years old, was appointed Lucasian Professor of Mathematics, succeeding his own former teacher, Isaac Barrow, who resigned the position specifically to make way for him. The post gave Newton a secure income and considerable freedom. Along with a lecturing duty, he reportedly discharged with little enthusiasm, occasionally addressing an empty room. According to accounts left by students of the period, through the 1670s, Newton built a reflecting telescope of his own design, using a curved mirror rather than a lens to avoid the color distortion that plagued refracting telescopes of the era, a device that brought him to the attention of the Royal Society in London. His subsequent work on light and color drew him into a long, often hostile correspondence with Robert Hooke, another leading scientist of the age whose rivalry with Newton would never fully cool. The achievement that secured Newton's lasting reputation did not emerge until the 1680s, and it took outside pressure to bring it into the world. In 1684, the astronomer Edmund Halley, wrestling with his own questions about the mathematics of planetary motion, travelled to Cambridge and asked Newton directly what shape a planet's orbit would take if it were pulled by a force weakening with the square of the distance. Newton answered, according to Halley's own later account, that the orbit would be an ellipse, a result he had already worked out years earlier, but never published or shown to anyone. Halley, recognizing immediately what Newton had solved, almost as an afterthought, urged him to write out the full proof, and personally covered the cost of printing it when Newton finally did. The result was Philosophiae Naturalis Principia Mathematica, published in 1687. Across 3 volumes, Newton set out his 3 laws of motion and his law of universal gravitation, demonstrating mathematically that the same force governing a falling apple in a Lincolnshire garden also governed the orbit of the moon and the motion of every planet around the sun. It remains one of the most important scientific works ever written, and it was researched, calculated, and largely composed within the walls of a single Cambridge college. Newton's later life pulled him away from Cambridge in practical terms. Though his formal ties continued for years, he became warden and later Master of the Royal Mint in London during the 1690s, pursuing counterfeiters with the same obsessive rigour he had once applied to mathematics, and served as President of the Royal Society from 1703 until his death, a position from which he continued his long, bitter dispute with Leibniz over who had truly invented calculus first. He also spent decades, largely in private, pursuing alchemical experiments and unorthodox theological study he kept carefully hidden from public view during his own lifetime. Activities that complicate the tidy popular image of a man remembered mainly for a falling apple. Newton died in 1727 and was buried in Westminster Abbey. The first scientist in English history granted that honour. But the room where his most transformative thinking actually happened was not the Abbey, and it was not even Cambridge itself during those crucial plague years. It was a farmhouse in Lincolnshire, made possible only because a university stable enough to survive plague closures had a fellow with the freedom, the funding, and the sheer intellectual momentum to keep working, even with its doors shut. Cambridge had spent 4 centuries of colleges, kings, and religious upheaval, building exactly the kind of institution capable of producing that outcome, without ever intending to produce Newton specifically. It was about to do so again, with a very different question, and a very different young man walking through its gates. Chapter 6. Empire, Enlightenment, and a Complicated Legacy. Richard Bentley was, by nearly every account, an extraordinary scholar and an exhausting human being to work with, and Trinity College's Master's Lodge under his 4 decades of leadership was rarely a quiet place. Appointed Master in 1700, Bentley brought a genuinely brilliant mind for classical scholarship into the role, pioneering methods of textual criticism that taught European scholars how to spot forgeries and later insertions buried inside supposedly ancient manuscripts, work that shaped how classical texts were studied for generations afterward. He also brought a personality that made enemies wherever he went. His 4 decades as master were marked by relentless disputes with Trinity's own fellows over college finances and his own authority. Disputes serious enough that in 1718 the university formally tried him and briefly stripped him of his degrees before restoring them. Genuine brilliance and genuine dysfunction shared the same corridors at Trinity under Bentley, sometimes inside the same person. And the university's records from this period read less like the biography of an institution, steadily accumulating wisdom, and more like an ordinary, quarrelsome workplace that happened to also be producing extraordinary scholarship. Newton's own legacy at Cambridge produced friction of a different kind. William Whiston, who succeeded Newton as Lucasian Professor of Mathematics in 1701, publicly declared his adherence to Arianism, a theological position rejecting the traditional doctrine of the Trinity, and was formally expelled from the university in 1710 as a result. Cambridge in this period still enforced strict religious conformity on its own faculty, even while its scientific work pushed steadily toward more open, evidence-based habits of inquiry. The Enlightenment did not arrive at Cambridge as a clean break from religious authority. For decades, the two coexisted, awkwardly, in the same rooms, contradicting any tidy narrative in which scientific progress and religious control simply traded places at some fixed date. Not every relationship from this era ended in conflict. Roger Coates, appointed the university's first Plumian Professor of Astronomy in 1707, took on the demanding work of editing the second edition of Newton's Principia, published in 1713, correcting errors and adding material under Newton's own supervision. Coates died in 1716 at only 33, and Newton is reported to have said, on hearing the news, that if Coates had lived, they might have known something, a line historians frequently cite as a measure of how highly Newton regarded him. The professorship Coates had held became a permanent part of Cambridge's growing scientific infrastructure. One of many endowed chairs the university added across the 18th century, quietly building the kind of stable, ongoing positions that no longer depended on any single wealthy patron's continued goodwill. A structural change whose importance would only become fully visible a century later, once Cambridge began competing directly with German universities in experimental science. That same century tied Cambridge more deeply into the economy of the British Empire, including its most morally indefensible feature. And this part of the story deserves the same care given to Newton's science, since presenting only one side of it would misrepresent what actually happened. A university-funded investigation, launched in 2019 and published in 2022, documented that individual Cambridge colleges had held investments connected to the transatlantic slave trade, and that the university had benefited both from gifts made by individuals who profited from enslaved labor and from academic work in the racial sciences that helped justify those systems intellectually. The findings were significant enough that the university issued a public apology in 2022 and committed funding toward research and outreach intended to address that legacy directly. It would be a mistake, though, to treat 18th century Cambridge as producing only complicity. In 1785, a student at St. John's College named Thomas Clarkson entered a Latin essay competition on the set question of whether it is lawful to enslave people against their will. He won the prize, and the story might easily have ended there. A clever essay, filed away and forgotten. It did not end there. According to Clarkson's own later account, He rode back toward London afterward, still turning the arguments over in his mind. And somewhere on the road, near Wandsworth, he stopped, dismounted, and sat down by the roadside, struck by the conclusion that if the horrors he had just spent months researching were real, somebody needed to do something about them, and that somebody might have to be him. He spent much of the rest of his life doing exactly that. Traveling England, gathering first-hand evidence on conditions aboard slave ships, evidence that was later used directly in the parliamentary debates leading to the Slave Trade Act of 1807. A university essay prize, intended purely as an academic exercise, had produced one of the abolitionist movement's most tireless researchers. Both of these threads, financial entanglement with slavery and the origins of one of its most effective opponents, ran through Cambridge during the very same decades, sometimes through the very same colleges. Neither one cancels the other out, and treating either alone as the whole picture would misrepresent what the historical record actually shows. Cambridge in the 1700s looked, in this particular respect, a great deal like Britain itself. A society capable of producing both the intellectual tools of the Enlightenment and direct financial participation in one of history's greatest moral failures, sometimes within the very same walls. By the century's end, Cambridge had built the professorships, the publishing relationships, and the international scholarly reputation that would let future breakthroughs draw on established infrastructure rather than depending purely on isolated genius. As Newton largely had, it had also built financial and intellectual ties to empire the university itself would not formally reckon with for another 200 years. Both of those inheritances were still waiting in the walls when a young clergyman's son named Charles Darwin arrived to study theology and spent most of his time chasing beetles instead. Chapter 7. The Heretic's Garden. Darwin arrived at Cambridge, intending to become a country clergyman. He left having quietly gathered the tools that would eventually let him rewrite humanity's understanding of its own place in nature. Charles Darwin arrived at Christ's College in January of 1828, and almost nobody who met him there, including Darwin himself, believed he was training for anything resembling the career that would eventually make him famous. His path to Cambridge had been reluctant and indirect. He had first tried studying medicine at the University of Edinburgh, but the anatomy lectures and unanesthetized surgical demonstrations of the period left him genuinely distressed, and he walked away before completing a degree. His father, worried that his son lacked direction, proposed the clergy as a respectable fallback, a common enough path at the time for a young gentleman without a clear profession, and Cambridge, with its close ties to the Church of England, was the obvious place to pursue it. Darwin later admitted in his own autobiography, with disarming honesty, that he spent a great deal more of his time at Christ's College riding, shooting, and collecting beetles than attending to his official theological coursework. Nothing in that record predicts a scientific revolution. A mediocre theology student with an expensive hobby is not, on its face, a promising biography. And the gap between what the record shows and what actually followed says something useful about how rarely consequential lives announce themselves in advance. That beetle collecting was not a passing distraction, though, and it brought Darwin, almost by accident, into contact with the one relationship that would eventually redirect his entire life. John Stevens Henslow, professor of botany, held informal gatherings for students genuinely curious about natural history, and Darwin became one of his most devoted regulars, spending so much time in Henslow's company that some of his own tutors reportedly began referring to him simply as the man who walks with Henslow. That friendship did not supply formal training in the sense a laboratory or a set curriculum would have. It supplied something arguably more valuable for what came next. sustained exposure to careful, patient observation as a discipline in its own right, modeled by someone Darwin respected and wanted to impress. Darwin completed his degree in 1831, and that same year, Henslow changed the direction of his life for good. The British Navy was preparing HMS Beagle for an extended surveying voyage to South America, and its captain, Robert Fitzroy, wanted an educated gentleman naturalist along, partly for scientific observation and partly, by Fitzroy's own account, for intellectual company during a voyage expected to last years. Henslow was offered the position first and turned it down for family reasons, recommending Darwin instead. Darwin's father initially refused permission, calling the voyage a waste of time for a young man meant to enter the church, and relented only after Darwin's uncle intervened directly on his behalf. Remove any one of these ordinary domestic details: a professor's family obligations, an uncle willing to argue with his brother-in-law, and one of the most consequential voyages in the history of science plausibly never happens at all. The voyage lasted from December of 1831 to October of 1836, carrying Darwin to the coasts of South America, the Galapagos Islands, and dozens of other stops along the way. Here it matters to be precise about something the popular version of this story often gets wrong, because getting it wrong changes what the story actually teaches. Darwin did not experience a single blinding moment of insight while standing among the Galapagos finches. His own notebooks from the period show him gradually working through the implications of what he had collected, developing his theory of evolution by natural selection over roughly 2 decades of careful observation, correspondence, and quiet revision, much of it conducted long after the ship had returned to England. From a study in the English countryside, rather than from any tropical island, the real lesson has less to do with sudden inspiration than with sustained, unglamorous patience. The same quality Henslow had modelled for him years earlier, on quiet Cambridge afternoons collecting specimens nobody else considered interesting. He delayed publishing that theory for years, fully aware of how completely it would conflict with prevailing religious and scientific opinion. What finally forced his hand arrived in the post in 1858. A letter from Alfred Russel Wallace, a naturalist working independently in the Malay archipelago, who had reached strikingly similar conclusions about natural selection entirely on his own. 20 years of careful, unpublished work was suddenly at risk of being overtaken by a stranger on the other side of the world. Darwin's colleagues arranged a joint presentation of both men's work to the Linnean Society in London that same year. And Darwin, prompted at last by the near-simultaneous discovery, published On the Origin of Species in November of 1859. The reaction split almost immediately along lines that still shape debates about science and religion today. Some scientists recognized the strength of Darwin's argument at once. Others, including prominent clergy and some scientists themselves, rejected it as a direct assault on the biblical account of creation and on humanity's special place within it. One of the most famous public confrontations took place in June of 1860, at a meeting of the British Association for the Advancement of Science in Oxford, where Bishop Samuel Wilberforce debated Darwin's supporter Thomas Henry Huxley. Exactly what was said that day has been disputed and embellished by different retellings for more than a century and a half, and historians examining the surviving accounts caution that no single contemporary transcript records the exchange word for word. What survived instead was the symbol, fairly or not, of a wider collision between traditional religious authority and the new evolutionary science. A collision this video will not try to resolve, since it remains a live and legitimate area of disagreement between religious and scientific worldviews rather than a settled historical question. Darwin himself never held a formal academic position at Cambridge after his student years, and conducted almost all of his mature scientific work privately from Down House, his home in Kent, corresponding with hundreds of scientists worldwide rather than lecturing from any university chair. His relationship to Cambridge differs meaningfully from Newton's in exactly this respect. Cambridge did not house the discovery itself. It supplied the mentor, the introduction, and the early formation that made the discovery possible. Years later, in a garden and a study, far from any college quadrangle, a pattern that will come up again with the third name on this video's thumbnail. Because not every Cambridge breakthrough happened inside a Cambridge building. Some of them simply started there. Christ's College still keeps Darwin's old rooms, and the college garden contains a mulberry tree long associated, by tradition, with his time there. A tradition the college itself is careful to describe as a marker of memory, rather than a claim of unbroken botanical proof. The same honest caution Cambridge applies to the apple tree outside Trinity. What can be said with certainty is simpler and, in its own way, more interesting. A young man arrived at Cambridge, intending to become a country clergyman, spent far more time chasing beetles than pursuing his official coursework, and left with a mentor, an invitation, and a habit of patient observation that would eventually reshape how humanity understood its own place in nature. Built over decades of quiet work rather than in any single flash of inspiration. Chapter 8. Steam, Suffrage, and the Cavendish. For its first 6 centuries, Cambridge changed at the pace of generations. The railway broke that rhythm inside a single decade. And the university's own reaction to it says something honest about how institutions actually behave when the future arrives faster than they are ready for. The Eastern Counties Railway reached Cambridge in 1845, and the university's first response was not excitement, but alarm. College authorities worried openly, in letters and committee minutes that survive from the period, that a direct rail connection to London would make it far too easy for students to slip away for entertainment. The university considered morally unsuitable. That anxiety reportedly shaped where the line actually ended up, with the new station built roughly a mile from the town centre rather than closer in. A compromise still felt today by anyone walking from Cambridge Station up toward the historic colleges. A university trying to solve a moral panic with urban planning is a small, almost comic detail. But it is also a useful reminder that institutions capable of producing Newton do not automatically become wise about every kind of change. The railway came anyway, and with it came faster mail, faster travel for visiting scholars, and a faster flow of scientific instruments and journals between Cambridge and the laboratories of continental Europe. That faster flow of information mattered enormously for what came next. A transformation built not around one genius, working alone in a rented room, as Newton largely had, but around a purpose-built laboratory designed to let many researchers work side by side. A structural shift in how science itself would get done at Cambridge from this point forward. In 1871, William Cavendish, the 7th Duke of Devonshire, and himself a Cambridge-educated mathematician, funded a new physics laboratory, driven partly by a sense that Cambridge, for all its reputation in pure mathematics, had fallen behind German universities in experimental physics. The Cavendish Laboratory opened its doors in 1874, and its first professor was James Clerk Maxwell, already recognized across Europe for unifying electricity, magnetism, and light into a single mathematical framework. Maxwell walked into a building with bare benches and no instruments yet installed, tasked with turning an idea that Cambridge could compete experimentally as well as theoretically into a working reality, essentially from nothing. Using his own considerable reputation to attract the funding and talent the laboratory would need to survive its first difficult years. Maxwell's tenure was cut short by cancer in 1879, when he was only 48, but the laboratory he helped shape outlived him by well over a century, becoming one of the most productive sites in the history of experimental physics. A fact that will matter directly in the next chapter of this story. What Maxwell and the Cavendish's founders had actually built, whether they fully realized it at the time or not, was an institutional answer to a limitation that had constrained even Newton. A shared, well-equipped physical space where instruments, funding, and researchers could be concentrated together rather than scattered across individual colleges and private studies. The very same decades that produced the Cavendish also produced one of the longest and most difficult struggles in Cambridge's history. The fight over whether women could study there at all. And this story deserves the same level of detail given to the physics, because both were happening at the same university, under the same governing bodies. At the same time, Girton College, founded in 1869, largely through the efforts of the reformer Emily Davies, and Newnham College, founded in 1871 under Henry Sidgwick and Anne Jemima Clough, gave women access to lectures and examinations for the first time. Access to an actual degree was a different matter entirely. One, the university would take nearly 80 years to resolve. From 1881 onward, women were permitted to sit the same examinations as male students, and their papers, marked without any knowledge of the candidate's identity, frequently placed among the strongest in a given year. The university's own examination system had, by its own internal standards, already proven these women's academic ability years before it was willing to grant them any formal recognition for it. Equal marks did not bring equal recognition. In 1897, when the university held a formal vote on granting women full degrees, male students gathered outside the Senate House in large, loud numbers, and contemporary accounts describe an effigy of a woman on a bicycle strung up from a window in mockery, a detail that captures the tone of the opposition more vividly than any summary could. The vote failed by a wide margin. Cambridge did not grant women full university membership and the right to an actual degree until 1948, more than 75 years after Girton opened its doors, one of the longest such delays among major British universities. Some women, unwilling to simply wait, found a workaround in the meantime, travelling to Trinity College, Dublin, in the early 1900s, where an arrangement allowed women who had completed the full Cambridge course of study to receive a genuine degree in absentia. Newspapers of the day nicknamed them the Steamboat Ladies. After the crossing they made to collect degrees, Cambridge itself still refused to award them. A detail that tells you the university's own resistance was well known enough at the time to become a running joke in the national press. A laboratory built to concentrate the university's finest experimental minds in one room. A nearly 80-year refusal to grant half the population the basic recognition every male student had received since the 13th century. These were not separate Cambridges. They were the same institution, in the same decades, sometimes governed by the very same men, capable of extraordinary innovation in one direction and stubborn resistance in another. The laboratory Maxwell built would go on, within a generation, to help uncover the structure of the atom itself. The women fighting outside the Senate House would keep fighting for decades more before the university extended them anything close to the same welcome. And this exact pattern, brilliant in one domain, badly behind in another, will reappear again before this video is finished. Chapter 9. Splitting the Atom. By the 1890s, the Cavendish laboratory had a new director, and under him it would become the site of one of the most consequential discoveries in the history of physical science. Discoveries that would eventually connect indirectly but unmistakably, to the invention of the computer that the third name on this video's thumbnail helped make possible. Joseph John Thomson, generally known simply as J.J. Thomson, was appointed Cavendish Professor of Experimental Physics in 1884 at just 27 years old, an appointment that reportedly unsettled some senior figures at the university, given his relative youth and a background leaning more toward mathematics than hands-on laboratory work. Thomson spent much of the following decade investigating cathode rays, the strange glowing beams that appeared inside vacuum tubes when a high-voltage current was applied, a phenomenon that had puzzled physicists across Europe for years without any settled explanation of what the rays actually were. In 1897, through a careful sequence of experiments measuring how these rays bent under electric and magnetic fields, Thomson demonstrated that cathode rays were made of particles far smaller and far lighter than any known atom, carrying a negative electrical charge. He had found what came to be called the electron, the first subatomic particle ever identified, quietly overturning centuries of assumption that the atom was matter's smallest, indivisible unit. Thomson received the Nobel Prize in Physics in 1906 for the discovery, and the Cavendish, barely 2 decades old at that point, had already produced a result that reshaped the foundations of physics and chemistry together. Thomson's own students went further still, and one of the more remarkable features of the Cavendish under Thomson was how deliberately he built a culture of mentorship into the laboratory itself, treating the training of the next generation of physicists as seriously as his own research. An institutional habit that would keep paying off for the Cavendish long after Thomson himself had retired. Ernest Rutherford, a New Zealander who arrived at the Cavendish in 1895 as a research student, went on to conduct the experiments at the University of Manchester that identified the atomic nucleus in 1911, showing that atoms were mostly empty space arranged around a tiny, dense, positively charged center. Rutherford returned to Cambridge in 1919 to take up the very same Cavendish professorship Thomson had once held, bringing with him a research style built on close, almost paternal mentorship of younger physicists and a relentless insistence on direct experimental evidence over elegant theorizing. Under Rutherford, through the 1920s and early 1930s, the Cavendish became, by the accounts of many historians of science, the single most productive center of experimental atomic physics anywhere in the world. In 1932, 2 researchers working under him, John Cockcroft and Ernest Walton, built an apparatus capable of accelerating protons to high energy and used it to bombard lithium atoms, splitting the nucleus of an atom for the first time by entirely artificial means, rather than relying on naturally occurring radioactive decay. The 2 of them watched a scintillation screen for the faint flashes of light that would confirm the nucleus had actually broken apart, a moment historians of science still describe as one of the quiet turning points of the 20th century. Cockcroft and Walton shared the 1951 Nobel Prize in Physics for that work, often described as the birth of experimental nuclear physics as its own distinct field. That same year, 1932, another Cavendish researcher, James Chadwick, identified the neutron, the electrically neutral particle sitting alongside the proton inside the atomic nucleus, resolving a long-standing puzzle about atomic mass that protons and electrons alone could not fully explain. Chadwick received the Nobel Prize in Physics in 1935 for the discovery, meaning that within roughly 3 years, a single laboratory on a single university campus had identified the neutron and demonstrated the first artificial splitting of the atomic nucleus, laying much of the experimental groundwork later drawn on by nuclear physics and, eventually, by nuclear weapons research during the Second World War, a connection the Cavendish's own physicists were acutely, uncomfortably aware of once that war actually began. Rutherford himself remained publicly skeptical. According to colleagues, that atomic energy would ever have any practical application, reportedly telling an audience in September of 1933 that anyone hoping to draw usable power from the transformation of atoms was chasing moonshine. Physicists who study this period often note the timing of that remark, since within roughly 24 hours, the Hungarian physicist Leo Szilard, reading a newspaper account of Rutherford's comment, began working through the concept of a self-sustaining nuclear chain reaction, an idea that would eventually underpin both nuclear power generation and nuclear weapons. One of the 20th century's most respected experimental physicists had publicly dismissed the very possibility that within his own colleagues' lifetimes would reshape global politics. A genuinely striking historical irony. Rutherford did not live to see how the science he had spent decades advancing would be applied elsewhere. He died in 1937, 2 years before the Second World War began. By the time that war arrived, the Cavendish had built, across roughly 60 years, an unbroken experimental line running from Maxwell's founding work in electromagnetism, through Thomson's discovery of the electron, to Rutherford's identification of the nucleus, to Cockcroft, Walton, and Chadwick's work on the atom itself. A single donated building, meant only to help Cambridge catch up with German experimental physics, had become one of the handful of places on Earth where the fundamental structure of matter was being uncovered directly, by hand, in real time. The next great Cambridge breakthrough would not come from a laboratory full of particle beams at all. It would come from a young mathematician at a different college entirely, thinking almost purely on paper, about what a machine could someday be made to calculate, and whether a machine could ever be said to think. Chapter 10. The War and the Birth of the Computer. Here, finally, is the third name from this video's thumbnail, and the story behind it is stranger than the word computer usually suggests, because for most of it, no actual computer existed anywhere in the world. Alan Turing arrived at King's College in October of 1931 to study mathematics, and within 4 years had produced a fellowship dissertation strong enough to make him, at only 22, one of the youngest fellows the college had ever elected. His most consequential work at Cambridge came not from any laboratory, but from a single theoretical paper, developed largely inside his own head and on paper, with no physical machine involved at all. In 1936, Turing published a paper titled On Computable Numbers, with an application to the Entscheidungsproblem, addressing a question the German mathematician David Hilbert had posed about whether a fixed, mechanical procedure could ever determine the truth of any mathematical statement. To answer it, Turing imagined a device, an infinite strip of tape divided into cells, read and written by a simple mechanical head following a fixed set of rules. This device, later called a Turing machine, was never built as a physical object in 1936. It existed purely as a thought experiment, a piece of pure logic worked out at a desk in a Cambridge college, in exactly the same abstract, solitary tradition that had once produced Newton's calculus in a Lincolnshire farmhouse. But it proved something extraordinary, that a single, simply defined mechanical process could, in principle, carry out any calculation any more complicated machine could about perform. Historians of computer science generally regard this paper as the theoretical foundation on which the entire modern concept of a general-purpose computer was eventually built. Even though the word computer, in the sense we use it now, appears nowhere in Turing's original text. Turing spent much of 1936 to 1938 away from Cambridge, studying at Princeton University in the United States, before returning to his fellowship at King's College shortly before war broke out. When Britain declared war in September of 1939, Turing was recruited almost immediately to the Government Code and Cipher School at Bletchley Park, some 40 miles from Cambridge, where a striking number of the codebreakers assembled were themselves Cambridge-trained mathematicians, chess players, and linguists pulled from the same colleges Turing had just left. Evidence of just how deeply the wartime intelligence effort ended up depending on Cambridge's peacetime talent pipeline. At Bletchley Park, Turing led the effort to break German naval Enigma traffic, building on earlier foundational work by Polish cryptographers who had first reconstructed the machine's basic operation before the war began. Turing designed an electromechanical device called the bomb, capable of rapidly testing thousands of possible rotor settings to identify the daily key the German Navy used to encrypt its messages. Historians studying the impact of this work, drawing on estimates the British government itself has since acknowledged, have suggested the code-breaking carried out at Bletchley Park shortened the war in Europe by a period some historians place at around 2 years, potentially saving a very large number of lives that would otherwise have been lost as the conflict dragged on. Though precise figures remain genuinely debated, given the impossibility of modelling a war that did not happen, what is not in dispute is that the work stayed officially secret for decades after the war ended, meaning Turing received no public recognition for it during his own lifetime, a silence that makes what happened to him next considerably harder to accept. His personal story after the war ended in tragedy that Cambridge and the British state itself have since addressed directly rather than quietly. In 1952, Turing was prosecuted under British law for homosexual acts, then still a criminal offence, and was sentenced to a course of hormonal treatment as an alternative to prison. He died in 1954, and an inquest at the time recorded the cause as suicide by cyanide poisoning. Though some biographers examining the case since have raised questions about whether the death was accidental, a debate that remains genuinely unresolved among historians rather than settled fact in either direction. In 2013, Queen Elizabeth II granted Turing a posthumous royal pardon, and in 2017, the British government extended an informal amnesty, sometimes called the Turing Law, to other men historically convicted under the same statute. King's College later established a permanent exhibition dedicated to Turing's life and work, part of a broader effort by the university itself to reckon publicly with how it had once treated one of its most consequential fellows, echoing, in a very different register, the university's own more recent reckoning with its historical ties to slavery. While Turing's theoretical foundations were being developed and then classified through the war years, a separate and more immediately visible Cambridge achievement was taking shape at the university's own mathematical laboratory. Maurice Wilkes, appointed its director in 1945 after wartime service in radar research, became convinced Cambridge should build one of the first genuinely practical working computers based on the stored program concept. The idea that a computer's instructions and its data could be held in the same electronic memory rather than fixed permanently into the machine's physical wiring. Wilkes and his team built the electronic delay storage automatic calculator, known as EDSAC, using tubes filled with mercury to store data as pulses of sound, a design chosen because more reliable alternatives were not yet widely available in post-war Britain. EDSAC ran its first program on the 6th of May, 1949, successfully calculating a table of square numbers, and in doing so became one of the earliest computers in the world to function as a practical, working machine that researchers could actually use for real calculations, rather than an experimental prototype that never left the lab. Cambridge researchers used EDSAC for genuine scientific work throughout the early 1950s, including early applications in crystallography and radio astronomy, cementing Cambridge's role not just in the theory of computing that Turing had supplied over a decade earlier, but in the physical, working machinery that finally made computing usable. Turing's paper and Wilkes's machine, read together, reveal something distinctive about this whole video. One achievement was almost entirely abstract, a thought experiment about an imagined device, developed by a young fellow with no laboratory at all. The other was almost entirely physical. Mercury tubes and vacuum valves wired together into something that actually calculated numbers. Newton's breakthrough had happened largely on paper. In isolation, 3 centuries earlier, Turing's happened the very same way. In a very different subject, 3 centuries later, at a different college in the same small town, Cambridge, it turns out, kept producing both halves of the same basic pattern. Abstract insight and physical machinery, generation after generation, joined by the same underlying tradition. Endowed colleges and laboratories stable enough to let people spend years working through ideas the rest of the world would not fully understand the importance of until decades later. Chapter 11. DNA and Silicon Fen. The 3 names on this video's thumbnail all belong to the past. What follows next shows how Cambridge kept the same pattern running well into the present, using tools none of those 3 men would have recognized. By the early 1950s, the Cavendish laboratory that had once identified the electron and split the atom had turned its attention to a very different kind of structure. One built not from subatomic particles, but from the molecules that carry the instructions for life itself. James Watson, an American biologist, and Francis Crick, a British physicist who had shifted into biology after wartime work on naval mines, met at the Cavendish in 1951 and began working together on the structure of deoxyribonucleic acid, already known to carry genetic information, but whose physical shape remained undetermined. Watson and Crick did not produce the primary experimental evidence that ultimately proved decisive. And this part of the story deserves to be told as carefully and completely as any other part of this video. That evidence came chiefly from Rosalind Franklin, a chemist working at King's College London, whose X-ray diffraction images of DNA, particularly a now famous exposure known as photograph 51, gave the clearest experimental evidence yet obtained of the molecule's helical structure. Franklin's colleague at King's College London, Maurice Wilkins, showed that image to Watson without Franklin's knowledge or consent, a fact that later biographers and historians of science, drawing on Watson's own published account and on Franklin's surviving papers, have treated as a genuinely uncomfortable part of this discovery's history, since Franklin received far less recognition during her own lifetime than the weight of her data warranted. Working from Franklin's diffraction data alongside their own model building at the Cavendish, Watson and Crick proposed the double helix structure of DNA in a short paper published in the journal Nature in April of 1953, describing 2 strands wound around each other and held together by pairs of chemical bases, a structure that immediately suggested how genetic information could be copied and passed on during cell division. Watson, Crick, and Wilkins shared the 1962 Nobel Prize in Physiology or Medicine for the discovery. Franklin had died of ovarian cancer in 1958, 4 years before the prize was awarded, and Nobel rules do not allow posthumous nominations, meaning she was never formally considered for a prize her own data had done so much to make possible. Cambridge has since taken visible steps to acknowledge that imbalance, including a research building at Newnham College named in Franklin's honor. Part of a broader pattern in recent decades of the university publicly revisiting figures whose contributions went under-recognized at the time. A pattern this video has now traced through Franklin, through the women fighting for degrees in the 1890s, and through Turing. The discovery helped establish the Laboratory of Molecular Biology, formally opened in Cambridge in 1962, which went on to produce a remarkable concentration of further Nobel Prizes across the following decades, in fields ranging from protein structure to genetic sequencing, becoming one of the most decorated single research institutions in the history of science. The pattern, first visible at the Cavendish a century earlier, endowed infrastructure, supporting concentrated expert research over long stretches of time, had simply carried over into an entirely new scientific discipline. The same institutional machinery applied to an entirely different problem. Cambridge's economic character began shifting alongside its scientific reputation in the second half of the 20th century. In 1970, the university published what became known as the Mott Report, examining how Cambridge might build closer links between its research and private industry. Recommendations that helped support the creation of the Cambridge Science Park that same year, one of the first university-affiliated science parks in Britain. Technology companies began clustering around the university through the 1970s and 1980s, drawn by proximity to Cambridge's research output and its steady supply of graduating engineers. A pattern commentators eventually nicknamed the Cambridge phenomenon, playing on the flat, marshy fenland surrounding the town. Silicon Fen, one company from this era, had consequences reaching far beyond Cambridge itself. Acorn Computers, founded in Cambridge in 1978, produced some of the most widely used home computers in British schools throughout the 1980s, putting a Cambridge-designed machine directly into the hands of a generation of British schoolchildren in a way EDSAC's own designers could hardly have imagined 3 decades earlier. In 1990, facing the technical limitations of existing processor designs for a new generation of computing devices, Acorn spun off a small design team to develop a new kind of energy-efficient processor architecture, a company that became ARM, later ARM Holdings. ARM does not manufacture chips itself. It licenses its designs to other companies instead, and according to figures ARM has published in its own financial disclosures, by the 2020 decade, chips, based on its architecture, were running in the very large majority of the world's smartphones, alongside a growing share of laptops and data center hardware. A processor design, first sketched by a small spin-off team in Cambridge in 1990, now sits, in some functional form, inside billions of devices used every single day around the world. An almost unimaginable distance traveled from a mercury-filled tube, calculating a table of square numbers, in 1949. Cambridge's more recent growth has drawn directly on this same combination of university research and nearby commercial investment. DeepMind, the artificial intelligence research company later acquired by Google, was co-founded in 2010, in part by Demis Hassabis, who had studied at Cambridge before completing his doctorate elsewhere. One example among many researchers whose formative training happened inside these colleges before their most visible commercial work happened outside them. Biotechnology firms, semiconductor designers, and artificial intelligence research groups continue clustering around Cambridge today for essentially the same reason. Technology companies began doing so in the 1970s. Proximity to a concentrated, continuously renewing supply of trained researchers passing through the same colleges that once housed Newton, Darwin, and Turing, a refuge for scholars fleeing violence in Oxford in the 13th century, had, by the early 21st century, become one of the most economically significant small cities in Britain. Its ancient colleges, sitting only a short walk from laboratories and technology campuses, working on some of the most advanced science and engineering being conducted anywhere on Earth. Chapter 12. Cambridge Now. The Unfinished Argument. It is early evening on a spring weekday, and a postdoctoral researcher in her late 20s is locking up her bicycle outside a genomics laboratory on the edge of the city, close enough to the fields that a tractor is visible, working the last light on the horizon. A scene like this one is illustrative, rather than a record of any single documented individual. Built from patterns that housing researchers and local reporting have described consistently enough that it is, in the most meaningful sense, true even without a name attached to it. She finished her doctorate here 2 years ago. She still cannot afford to live inside Cambridge itself. So this evening, like most evenings, she will cycle to the train station and commute out to a smaller town where her rent is something close to survivable. According to figures published by the Office for National Statistics and cited repeatedly in local reporting through the 2020 decade, average house prices in Cambridge have climbed to a level requiring a multiple of local average earnings, well beyond what most residents, including a large share of university staff and postdoctoral researchers, can realistically afford, making Cambridge one of the least affordable cities in Britain relative to local wages. Some of the city's own councillors and housing researchers have described this affordability gap explicitly as a threat to the very research economy the city depends on, since the technicians, junior researchers, and support staff who keep the laboratories running are increasingly priced out of the city where they work. That tension is, in its own modern clothing, the same argument Cambridge has been having with itself since the earliest years after 1209, over who the city and its university actually belong to, and who gets pushed to its edges in the process. The university has spent recent years examining its own past more directly than it did for most of its history. Individual colleges have commissioned their own reviews of specific benefactors and historical practices, following the pattern set by the university's 2022 report on ties to slavery. And funding has expanded for outreach programs intended to bring students from a wider range of economic backgrounds into a collegiate system that, for most of its existence, served a narrow slice of British society almost exclusively. Whether these efforts genuinely close the gap they are meant to address remains an open question. One current students, faculty, and outside researchers continue to argue about without any settled consensus. The same kind of unresolved argument that ran through the fight over women's degrees, through Turing's pardon, and through Franklin's belated recognition. Walk from that same genomics laboratory back toward the historic center on any clear evening, and you cross, in perhaps 20 minutes, roughly 2,000 years of the same underlying pattern. The river still runs past Castle Hill, where a Roman surveyor once judged it narrow enough to cross. King's College Chapel still stands with its stained glass, exactly as it was finished in 1531. Trinity College's Great Court still surrounds the rooms where a young Newton once worked through calculations that would eventually explain the motion of every planet in the solar system. And the apple tree still grows outside the chapel, tended as a living echo of a story that happened in a Lincolnshire garden rather than here. Christ's College still keeps the rooms where Darwin spent more time chasing beetles than attending to his coursework. King's College still holds the archive built to honour a fellow the British state once prosecuted and only much later pardoned, and a short walk from all of it. Laboratories and technology offices keep working on some of the same fundamental questions. In physics, in biology, in computing, that first gave this small market town its outsized reputation. Newton did not arrive expecting to explain gravity. Darwin did not arrive expecting to explain the origin of species. Turing did not arrive expecting to lay the theoretical foundation for every computer built afterward. None of this accumulated according to any single coherent plan. It built up, crisis by crisis, and generation by generation. From displaced scholars looking for somewhere safer to work. From institutions built to survive disasters rather than to prevent them. And from a river crossing that, for 2,000 years, kept being the place where people who needed to think, to build, or simply to cross safely from one side to the other, decided to stay a little longer than they meant to. Each of the 3 men on this video's thumbnail came to this small town for reasons that had nothing to do with the thing he would eventually be remembered for. And each of them found here, in an endowed college with centuries of accumulated stability behind it, exactly the kind of quiet, protected room a genuinely original idea needs in order to survive its own first fragile draft. The postdoctoral researcher reaches the train platform just as the light finally goes. Behind her, across the river, the lit windows of a laboratory are still on. Someone still working late on a problem nobody outside Cambridge has heard of yet. Cambridge cannot promise that whatever is happening behind those windows tonight will matter the way Newton's calculus mattered, or Darwin's finches, or Turing's tape machine, but it may still be giving someone, somewhere inside those lit rooms, the quiet space to ask a question the rest of the world has not noticed yet, which is, when you trace this whole story back far enough, the only thing this small town on a flat stretch of eastern England ever really had to offer anyone